First, I'd like to say thank you to Jinhyun Park for hospitality and giving me a chance to talk here. Okay. So today I'm going to talk on the recent progress on algebraic cycles. And now let x be a projective and smooth variety over field F. Then the subject of this talk is the child group, which is defined as a quotient of algebraic cycles on X of codimension R modulo or rational equivalence. Okay. And in recent years, there has been a significant progress on motivic homology, and by Voevodsky, Morel, and so on. In
your field is any characteristic?
Yes, any field. But I keep in mind F is a number field or a periodic field. Periodic field of characteristic 0. Okay. And in terms of the motivic theory, this is equal to the motivic homology groups. This is a Voevodsky. Okay. So the child group behaves like the cohomology groups, but I will not go on the general theory on motivic cohomology groups. Today I focus on the only child groups. Now there is a big conjecture on child groups. The finiteness conjecture, which says if the base field F is a number field, then the child group is a finitely generated Z module. Okay. And also there's an analogous conjecture for motivic cohomology groups, which is called Bass conjecture more generally. If X is a regular and of finite type over OF. OF denotes the integer mean. And then the motivic cohomology group is conjectured to be finitely generated Z module. But we don't go on the general conjecture. Okay. Now let's take a look the case codimension 1, R equal 1 case. This is the simplest case. Okay. In this case, it's known that there is an exact sequence from Picard variety to the child group and the Néron-Sévère group. Okay. And this is the Néron-Sévère group, and it's known that this is a finitely generated Z module. For this is true for arbitrary field. Arbitrary. even for a positive, even for positive characteristic. Okay? And this is the Picard scheme. It's a Picard variety. Picard variety, which is a abelian variety of a number field F, and then the valued point, F valued point of the abelian variety is known to be the finitely generated Z module by the famous theorem of Model and Bay. Okay. So the conjecture, the finiteness conjecture is okay in case R equals 1. Okay. But if R is, greater than 1, then it's a widely open problem. Widely open. And so far, there's no general results on this conjecture. Right. And so today, so the conjecture is very difficult, too difficult, and so people consider the more weaker questions. So first, people consider the same questions about when the base field is the p-adic local field. What about so the question now assume that F is a p-adic field. Namely, it's a finite extension of QP. Okay. Then, so let's see the R equal 1 case again. And the Néron-Serre group is still finitely generated D module. And this group is described by the classical theorem of Matuk. The theorem, the Matuk theorem, and it's an old theorem, which says let A be a abelian variety over field F. Here F is a finite extension of QP, and let G be a dimension of A. So then the valued point of A is isomorphic to the OF plus G plus some finite group. Okay. OF is a integer ring. So we see that the child group is no longer finitely generated Z modules because this is a big abelian group. But the following still remains true. Okay. So the first of all, mod n, Chao 1 mod n is finite. So question 1 is finite. Okay, this is to when R equals 1. And question 2 is Chao R torsion is finite when R equals 1.
Question 1, what do you mean by n?
n is arbitrary. It's arbitrary n for n. Yeah, integer. Yes. Okay. Okay. This is the base field is finite case. Is a finite extension of QP. Right. Okay. And recently, Shuji Saito and Kanetomo Sato obtained a general result about the question 1. Okay. The theorem of Shuji Saito, and Kanetomo Sato. Okay. They obtained the following theorem. Now let X be a spec OF. F is a periodic local field. And projective and semi-stable semi-stable scheme over OF. Namely, this is a projective and flat morphism such that the generic fiber is smooth and the special fiber is the script X is a regular scheme and the special fiber is a normal crossing divisor in X. And let D is a relative dimension over X. And n is an integer such that which is prime to P. Then they prove that Chow D X mod n is isomorphic to the arc homology D mod n D. Okay. And now the base chain theorem of étale cohomology groups. This is isomorphic to étale cohomology of the special fiber. So Y is a special fiber. D mod n D, and this is known to be finite. This is a finite group. So this is a finite group, and there's a surjective map from X O F to F to this one. So we have this group is finite. So, okay. Okay. Here's a brief introduction. Okay. Shuji Saito was my advisor. And Kanetomo Sato is my colleague, and we are in the same grade, and we are the students of Shuji Saito. Okay. So the teacher and the students. All right. Okay. And now I remember that Shuji completed their proof 2005 probably. In the same year, Seminar. Okay. So the last July, there was a big conference of Regulator 3. Regulator 3, and 2010. Okay. in Barcelona. And before Regulator 3, there was a conference, Regulator 2. It was 2005 in Banff. Okay. And Shuji gave a talk on this theorem this year at the conference Regulator 2. And at the same conference, Andreas Rosenshon announced the following counterexample to the question 1. Okay? So the Rosenshon 3 inverse. Okay? And they constructed there exists some threefold over some periodic field, and the elliptic curve such that Chow2 not L is infinite. Okay, so okay, this it's L is also a some L. Some L. L is a prime number. Such that, and Chow3 W cross E, the L torsion is infinite. So this notation means the kernel of the multiplication by L.
So L must be different from P.
Possibly L equal P. Yeah. But it's some L, right? Well, yeah, anyway. And I was also in this conference Regulator 2, but I remember that he at that time he didn't have a complete proof. He only announced, and he said it's almost theorem. But I think he completed the proof half a year later. And yeah, and naturally Shuji had a great interest in his talk, and he asked many questions to Rosenshon. And I didn't pay much attention to his talk, but I was in the conference, and at the hotel room, I computed some K2 symbols and stimulating computations, and then I realized one technique for computing regulator, okay, a new idea, and I didn't tell it to anybody, but after half a year later, I emailed to Shuji my computations. And then Shuji also had a great interest in my computations. And he asked many questions to me. And finally, he found a mistake in my computations. Okay? And he also fixed my mistake. And he also pointed out we can construct a new counterexample to the question 2. Okay? So this is So we have a theorem, Shuji Saito, and myself for L not P, and myself for L equals P. Says there exists a surface such that the tau 2 x L primary torsion is infinite. And this means union of the kernel of L to N. Right. Right. And in the joint paper with Shuji, we use the theorem of Sato in the proof in the proof here, but recently I removed the condition L not equal to P, and then there I didn't use their theorem. Okay. Okay. Now the counterexample. So now we have a counterexample to both questions, but the counterexample, our counterexample, are not defined over a number field. Okay, not defined. Namely, the minimal field of definition of X or W or E is not a number field, contains a transcendental number over Q. So it naturally leads the following revised questions. Question revised. Okay. Now let X be projective smooth variety over a number field. And let F3 be a completion at a finite place V. So then shall R X cross F V mod N and shall torsion subgroup finite. And so far, there's no known counterexample to this revised questions, and very few things are known so far. There's only one affirmative example. Affirmative. This is a Kanetomo Sato and myself, and let phi Q is an elliptic case-free surface. Case-free surface, and such that general fiber is plus zero, then chow 2 x delta q qp torsion is finite. For p is 7, 11, 19, 23, 31. Okay. So this is the only known example to the revised question. Okay. All right. And so this is the second visiting to Kai, second visiting to Kai, and the first visiting 2 years ago. Yeah, 2 years ago. Yeah. So, 1.5 years. And I gave a talk on this theorem. So this is the, okay. Anyway, okay, so the rest of the talk, I'd like to explain how to attack the torsion. Torsion of the cycle. Okay. So last month I met Kanetomo Sato, my colleague, and he visited Hokkaido University, and we had a dinner, and there he complained that people don't understand. This is not the study of torsion cycles. Okay. This is not the study of the torsion, but the study of the regulator. So I'd like to explain it. Okay. Now let F is a number field, or a periodic field, finite extension of QP. Okay. Then so the by is Merklef-Susselin theorem. Merklef-Susselin theorem plus Bloch-Rogas theory. There the following exact sequence. And this N denotes the kernel. The generic point of X. Okay. So this is the definition. Okay. And this is a K cohomology, and this is a K cohomology. K cohomology. Or if you like the higher Chow group, this is written that X1. Shall I define this group? No? Okay. Okay. It's a some group. Okay. And this is a map. This is a regulator map. To the ASARC cohomology group. Okay. So the study of the torsion of the Chow group, torsion part of the Chow group is equal to the study of the regulator map. But here, this NH3, this is difficult to compute. But here's a nice lemma. Here's a nice lemma. Now NH3 XQL2 is contained in the ASARC cohomology group, okay, by definition. And there's a map to the H1, Galois cohomology. Okay. Now let the composition is phi. Let denote phi. Then there's the following lemma. So the image of phi is contained in G part of QL2. Okay, so this is a G part of block cutter. Okay. G part. So therefore, the corollary, as a corollary, can I use this word? Theorem. This is originally due to the Langer and Shuji Saito. Is a good reduction case. Reduction at F. And Kanetomo Sato and Shuji Saito, the general case. If the regulator map on H1 XK2 is QL to the regulator map, and G is surjective, and then the Chow group of the L primary torsion is finite. Okay. And I remark that if F is a number field, then regulator is block cutter conjectures that leg is bijective. Okay. So therefore, the study of the torsion cycle is a part of the study of block cutter conjecture. Okay. And now, we see more details. And okay. This is a ASARC homology, second ASARC homology group. This is decomposed into the Néron-Severi group, tensoring with QL1, plus its orthogonal complement. Complement. And there's also a corresponding decomposition is on H1K2, namely is the decomposable part plus indecomposable part. So I will not explain what are they. Anyway, there's a map, the regulator map to the G part of the GF to H2 X bar QL2. Then the decomposable part is going to the G part of GF to the Néron-Severi group QL1. And the indecomposable part is going to the G part of coefficient V. Okay. And so this factor is almost isomorphic to the QL1, direct sum of QL1. Okay? Because, for example, the Néron-Severi group of X bar is generated by F rational cycles, then the Gara group acts on Néron-Severi trivially. So this is exactly isomorphic to the direct sum of QL1. Okay? But more or less, it's easy to describe. So, so this homology group is easy. Namely, it can be computed by the Kumma theory, and this part is there's no easy way to compute. It's a difficult part. Okay. So the essential difficulty is the construction of indecomposable elements in H1 G V. Right. And H1, let's see more. GF, there's another part which is called F part. FV is the F part of block cutoff, or it's often called the Selma group by block cutoff. The Selma group or Selma group of block cutoff. And the fact, there's a fact, the standard fact, if F is a finite extension of QP, then H1G, GF, V, the H1F is contained in the H2 crystal homology group. No, sorry. It's no. OF is the and F is a Now F is a finite unnatural extension of QP. Then this is isomorphic to the following group. No, I. So more or less, it's compute. It's rather easier to compute. Okay. But the Selma group is more difficult, the most difficult part. And there's no easy way to describe this group. Okay. And example, for example, now let E is an elliptic curve over F. Then the F valued point of E is into the Selma group of F to TPE. And this is an analogy of the H1 xk2, the integral part. I will not explain it. The cell, no, not injective, but anyway, there is a map to the F way. Okay, and so usually it's difficult. It's difficult to show the surjectivity of this map. Okay. Yeah. Okay. And the same difficulty appears in our situations. Okay. So that's the difficulty. Okay. Now, yeah, okay, I stop here.
There's a question.